All right, good morning. That's good. All right, so I got the course calendar pulled up here. Let's take a look at what's going on. Today we're going to cover the last new lesson this semester out of Appendix H on complex numbers. And then next week we'll spend the whole week, Monday, Wednesday, Friday, doing review for the final exam. Notice that next week you have no quiz, but you do have one homework due. And there will be more review going on in recitation as well. Okay? Now for next week's review, I think the best thing we should do is to look at the two most recent final exams. So start working on the one from spring 2015. That's this one right here. And the one from fall 2014. Okay? So start working on those two. It doesn't matter which one you want to start, but at least start looking at them. And even if you don't get to work on any of them by Monday, at least look through both of these exams and circle the ones that you think are going to be most difficult for you, and then let's spend more time on the most difficult ones in class, as opposed to working out them one by one. Sounds good? Okay, good. Okay, so we're going to be looking at Appendix H on complex numbers. Now you don't really see complex numbers in Calc 3, but as you continue beyond that, when you take things like differential equations or in your own major course such as electrical engineering, even in aerospace engineering, this stuff comes up. So this will come up later on in your Purdue career. So now is a good time to get used to it. And many of you have seen this before. Okay? So we define the number square root of -1. We'll call that I. This is what's called the imaginary number. It's a number that we can't deal with, but we give it a name, and we pretend we can deal with it. And then we look at the consequences of what happens when we include this as part of the numbers that we ordinarily work with. When we say a complex number, we talk about a number that looks like this. Normally, we give the variable name as z. That's a very standard variable name for complex numbers. And it looks something like that. Okay, where a and b are constants, so you have a real number here, and then a complex number, so that's b times I. A is called the real part of the complex number z. And b is the imaginary part. And we often plot these numbers on what's called a complex plane. It looks like the x and y's plane. But what we do instead of x and y, the horizontal axis is the real part of the number, and very often abbreviated as RE for the real part. And then the vertical axis is reserved for the imaginary part, IM. Okay, so the number, let's say z1 is equal to 3 plus 2i. It has a 3 as its real part and a 2 as its imaginary part. So it would sit right here. Right? That's one point in the complex plane. Put another one down here. Minus 1 minus 4i, let's say. So this would have a minus 1 as the real part, and then a minus 4 as the imaginary part. Okay? And when you look at this, it looks kind of like how we deal with vectors, right? And in fact, there are many things we can do to complex numbers that we can also do to vectors. And we'll see some of those similarities in a little bit. Okay, let's see how we can add and subtract complex numbers. For example, 3 minus 5i minus 8 plus 9i. I got one complex number, 3 minus 5i, and I got another one, 8 plus 9i. I would like to find the difference between the two. And this is pretty intuitive. You group all the real numbers together, you add them together, you group all the complex numbers together, and you combine them, just like vectors, right? You take your I component of vector, put them together, you put your J component, put them together, exactly like vectors. So let's put the real ones together, 3 minus 5, that's my real. And then my imaginary ones are minus 5i, minus 9i. So this is minus 5, minus 14i. All right, so that's pretty easy. That's how you add and subtract complex numbers. Exactly, just keep in mind, exactly like how you deal with vectors. Let's look at now how we can multiply complex numbers. And it's pretty easy when you're multiplying a complex number by either a real or imaginary number. Like in this case, this is a complex times a real, right? So this is pretty easy. 6 minus 10i. A complex times an imaginary. And this is still also pretty intuitive. 6i minus 10i squared. Right? And what's I squared? That's right. So this becomes plus 10, right? Remember, the definition of I is the square root of minus 1. So if I square I get minus 1 back. If you're multiplying two complex numbers together, then you do the usual thing you do with binomials. You FOIL this out. So we get 3 times 8 plus 3 times 9i plus minus 5i times 8 plus minus 5i times 9i. So this is 24 plus 27i minus 40i minus 45i squared. But I squared is minus 1, so this is really plus 45. Adding the other 24 is 69 minus 13i. Right? Okay, so that's how you multiply these numbers. Pretty easy. Oh, let's do one more multiplication here. Sometimes the I is not explicitly written out. So like in this case here, we have radical minus 9 times radical minus 16. So if you break these things apart, then you can see it as radical minus 1 times radical 9, and then radical minus 1 times radical 16. And that gives you 3i times 4i, and it gives you minus 12 when you multiply these things out. Okay? Okay, any question on multiplication before we move on to division? Nope? Good. Now let's divide stuff then. Division. And just like in multiplication, if you're simply dividing by a real number or an imaginary number, it's pretty straightforward. It gets complicated when you divide a complex number by another complex number. So let's go directly to that case. Let's see what we end up getting if we divide 2 plus 7i by 9 plus 5i. The end goal here, what we're trying to accomplish here, is to rewrite this quotient as in this form right here, a plus bi. So in other words, we need to know what the real part of that division ends up giving us and what the imaginary part is after we do the division. And then we can put it together. And in order to do that, basically what we need to do is to eliminate a complex number from the denominator. If we could accomplish that, then we can deal with this very easily. So here's what you do. You look at the denominator here. You keep the numbers themselves, but you switch the sign. I have 9 plus 5i right now. I want to multiply top and bottom by 9 minus 5i. This is called a complex conjugate of 9 plus 5i. Okay? And the notation looks like this. If you put a bar, straight line over the entire number here, this means you want to find the complex conjugate. So this is 9 plus 5i complex conjugate. That's 9 minus 5i, right? And suppose we have 10 minus 3i. Then its complex conjugate would be 10 plus 3i. Okay, so if you do that, every time you get a number like that, multiply top and bottom by the complex conjugate of the denominator, and then carry out the multiplications. Right? So let's multiply things out. The numerator is going to give me 18, 2 times 9, minus 10i, plus 63i, and minus 35i squared. Right? And then the denominator is 81 minus 25i squared. Then simplify. I squared is minus 1, so this is 18 plus 35, 53, minus, rather plus 53i. Downstairs, I squared is minus 1, so this becomes 81 plus 25. It's 106. And so that's also equal to 53 over 106 plus 53i over 106, or 1/2 plus 1/2i. Okay, so in the end, we started with a fraction of two complex numbers, but then after taking the step by multiplying top and bottom by the complex conjugate of what's in the denominator, eventually we end up getting a plus bi. Okay, questions? Nope? Good. Let's talk more about these things. Go to the general case. When we have a complex number a plus bi, the absolute value or the modulus of a complex number is equal to the real part squared plus the imaginary part without the I here. Notice I doesn't show up here. Just the number in front of the I squared and then under radical. Okay, so that's called the absolute value or the modulus of a complex number. Note this number is always real. I doesn't show up anywhere in the modulus. The modulus of a complex number is always real. Okay, so now where did this come from? When you look at this equation here, does it remind you of something that's very basic that we always deal with? Pythagorean theorem, exactly. That's where it came from. So a plus bi sits on the complex plane right here. If you complete a triangle here, the base of the triangle, of course, is A. The height of the triangle is, of course, B. The hypotenuse is the modulus. And as you can see, this is exactly how we would find the length of the third side here when we do a triangle. So this came directly out of Pythagorean theorem. And this is also how you find the magnitude of a vector. So again, in many ways, you can treat a complex number almost just like a vector when you're dealing with the magnitude and adding and subtracting them to get stuff. Another property of the modulus if you multiply a complex number by its own complex conjugate, you get the modulus squared. Okay? So it's very easy to see how that works. Here's my complex number. Multiplied by its complex conjugate. So we then get a squared minus b squared I squared. And it turns into a squared plus b squared. And if the radical of this thing is the modulus, then this thing by itself must be the modulus squared, right? Okay, so that's the modulus of a complex number. Questions? Nope, it's pretty simple stuff. It gets very fascinating when you start doing calculus with this thing. But to do that, you need to first take calculus 3 before you can deal with calculus of imaginary numbers. It's kind of fun if you ever want to do something interesting or whatever. Okay, let's look at next the powers of I. And I'm sure many of you have seen this before. We know I to the first power is I, right? We know I squared is minus 1. I cubed is I squared times I, so negative I. And I to the fourth is I cubed times another I, so that's minus 1, positive 1. I to the fifth is this times I, so that's I again. I to the sixth is I times I, negative 1. I to the seventh is minus I. I to the eighth again is 1. So looking at this here, the pattern is clear. After every 4 powers of I, this thing repeats again. So I to the 9th would be I to the 10th would be minus 1, right? I to the 11th is minus I, and I to the 12th is 1. And then this continues again. So as long as you know the first 4 powers of I, anything after that, it just keeps cycling around. So if you ever want to find the 21st power of I, you could keep counting this 21 times, 1, 2, 3, 4, 5, 6, 7, 8, 9. You can do that, that's fine. Or you can be a little bit more smart about what you're doing here. Think of it as I to the 20th times I to the 1st. And I to the 20th is I to the 4th to the 5th. But we know I to the 4th is 1. So this turns into I, right? Another way to do it is to divide the power by 4 and keep the remainder. The 21st power divided by 4 gives me 5 with a remainder of 1. And that's all that matters. You collect the remainder and make it a power of I. And these two things will be identical. So we end up getting I. Because what this is saying is that we complete 5 cycles of 4. We do this 5 times. And then we go one more beyond that. And it's really the one that we go beyond every cycles of 4 that matters to the power of I. Okay? So that's another way to find powers of I. All right, so now you try this. Tell me what I to the 126 is. One, two, three, 4, 5, 6, 7, 8, 9, 10. That take a while. Let's do a smarter way. Tell me what I to the 126 is. Okay, who's got it? What do you got? Minus 1. Everyone agree with that? Okay, so how did you do it? Right. Yeah, absolutely. So 126 divided by 4. So I have a remainder of 2, right? So this is I squared, and that's minus 1. You could also do what I did earlier by decomposing this. This is I to the 1/20th times I to the 6th, which is I to the 1/20th, I to the 4th, I squared. And that's 30 complete cycles of 4. So that's a 1. That's a 1. And this will give me just I squared, or minus 1. Okay? Now, if you start allowing complex numbers, then we can find more roots to polynomial equations. So for example, if we start allowing the complex numbers to be used, then we can find out what x can be, real or complex. Now we can allow x squared to be negative. If we only restrict ourselves to real numbers, x squared can never be negative. But now we're going to let it happen. So we get the usual plus or minus 2, and we also get 2 more roots, plus or minus 2i, right? So in general, we always get the same number of roots as the power of the equation when you allow complex numbers. If you only allow real numbers, we don't get that many. It's up to that. But allowing complex numbers, we can get up to, always equal to the number of the highest power there. Look at a quadratic equation. And this thing has no real solutions. If you try to factor this, if you use quadratic formula, for example, and you do not admit imaginary numbers, it has no real solutions. But once again, if you start allowing complex numbers to be considered, then we can expect 2 solutions. All right, so let's use the quadratic formula here, minus b plus or minus b squared minus 4ac all over 2a that's a negative 3, right? So we end up getting minus 5 over 2 plus or minus root 3 over 2i. And here are the 2 solutions we expect because the power is 2, and they're both complex. And here's a very important thing to remember. Complex roots always show up in conjugate pairs. In other words, you either get 0 complex roots here, or you get 2. You can't get 1. They cannot show up in isolation. Look at the previous one here. We have our plus and minus 2i. These two form a conjugate pair. So 2 real and 2 imaginary. And these always show up in pairs. So if you solve a cubic equation, what are the possibilities in terms of the roots? All real, yep, that's one possibility. What else? Two complex, yep. One real, right? What else can it be? That's it, isn't it? Right? They're all real, or 2 of them are complex. Because we can't just have 1 complex. We can't have 3 complex. So either no complex or 2 complex. So these are the only possibilities. Now let's look at the polar form of a plus bi. Remember, this is r as a function of theta. Right? The distance from the origin and the angle measured from the horizontal axis. That's the polar coordinate. So if we go back to the triangle and use Pythagorean theorem again, we can find r right away. R is pretty easy to find. And that's nothing more than the modulus of the complex number z. Now let's look at the cosine and sine of this angle. Cosine is adjacent over hypotenuse. So a over r. So that means a is equal to r cosine theta. Then look at the sine of theta. It's opposite over hypotenuse. And so b is equal to r sine theta. Now, if I replace a and b in the original equation by these 2, then I would get my polar form. So a is r cosine theta plus b r sine theta. Now, normally, very often you'll see this I put in front of the whole thing. So instead of writing as r sine theta I, very often the I is put way in the front. And that's just for one reason, is to make it very, very obvious that the second thing is an imaginary part, imaginary number here. So simplify this a little bit more. We get r cosine theta plus sine I sine theta, or modulus z cosine theta plus I sine theta. R is called the modulus. Theta also has a special name. It's called the argument. And it is written this way too. Theta is the argument, ARG, of Z. Okay, so this is how you convert any number, any complex number in the form of a plus bi into the polar form. So right-hand side is a function of theta, and this is a number. So you achieve the objective there. All right, the last thing we're going to look at is complex exponential. We know from the Taylor series of E we can write e to the x as an infinite series, 1 plus x squared over 2 plus x cubed over 3 or x to the n over n factorial. So now let's let x become an imaginary number. In fact, we'll write it as I times y, where y is some number. Okay? And we're going to reuse that formula here. So the first one doesn't change. The second one is IY. And then 1 over 2 factorial IY squared plus 1 over 3 factorial IY cubed plus 1 over 4 factorial IY fourth, and so on. Now look back to the powers of I. Notice that all even powers of I are real. All odd powers of I are imaginary. So this is real, right? This is real. That's imaginary. That's an even power of I. This is real. That's an odd power of I. This is imaginary. This is real. Next one is imaginary, and so on. See that? Now let's collect all the real ones together. So we get 1 plus this I squared is minus 1, right? And I to the fourth is positive 1. The next one is I6. That's negative 1 again. The next one is 8. That's positive. So these are the real ones. And now let's collect all the imaginary ones. First one is y, and this is a negative y cubed over 3 factorial. I pull the I out in the front. The next one is I to the 5th. It's this times negative 1. So switch your sign back to plus. And then switch your sign again when we go to the next one, because each one is an I square beyond it, which is minus 1. So they flip signs. All right, now do you recognize what this first one, the real, all these things put together, the real stuff. This is a Taylor series of something. Anyone recognize what this is? It's one of the trig functions. It's a cosine. And how do you know? When y is 0, we know cosine of 0 is 1, right? So we need to get a 1. So this first group here is cosine. This other one is sine. So that formula right there is called Euler's formula. If you let y be pi, then you get this equation. And have you seen this before? That either of these two? I'm sure some of you might have seen it before. This is called Euler's identity. It's a pretty famous formula. Euler discovered the result and blew his mind. But what happened here is it's a unification of a bunch of basic mathematical things. E is from calculus. Pi is from geometry. I is imaginary number. 1 and 0 are numbers we count with. So this one formula here unites a bunch of different branches of mathematics that people used to think were completely separate. People before calculus we have today, people couldn't make the connection between calculus and geometry. And now we can do that using analytic geometry, which is the basis of calculus, to unite the two. But this one equation here fascinated him very much because it's a unification of a bunch of stuff. All right, so that wraps up 162. Okay, next week we will do review. So start looking at the two old exams I mentioned, fall 2014 and spring 2015. See you next week.